One of the most common motions in nature is the harmonic oscillation, in which an object oscillates around an equilibrium point. This can be either a tennis ball on a spring, or it can also be, for instance, an object moving in a pendulum motion. In this lecture, I'll tell you why the harmonic oscillation is so common in nature, and I'll show you an important mathematical tool to solve the equation of a damped harmonic oscillation. And for that, we will use the concept of a phasor. A phasor is a complex number in radial coordinates, which means that if you have the imaginary plane, the complex plane, real part, imaginary part, and you plot a quantity a plus bi, you normally draw a point in this complex plane. A is the real part, b is the imaginary part thereof. But of course you can also write it in a radial representation where you talk about the amplitude of the complex number and the phase of the complex number, and the relations between this a, b and the amplitude and phase are of course the easy ones. So this quantity is what we call a phasor. Now you might wonder, why are phasors useful? The most important reason why phasors are useful is that the relation e to the power I phi is cosine phi plus I sine phi, which already indicates that there is a relation between this complex exponent and cosine and sine harmonic functions. So if you ask me why phasors are useful, I would give three reasons. The first one is this relation that I just mentioned, e to the power I phi. The second one is that exponents are easily to differentiate, right? Because if you take the derivative of e to the power I phi, you get I times e to the power I phi, as indicated here. And the third one, of course, is that complex numbers are not that difficult to calculate with, because you have the relation I squared is minus 1. One example of the use of phasors is based on this relation. So suppose you want to calculate the cosine of the sum of two angles, and you want to express this in sines and cosines of the individual angles. How do you do that? Well, what you use is the relation that you can write the cosine as the real part of a complex exponent. And a complex exponent you can express as the product of these two complex exponents. Now if you take one of these exponents and write it back into cosine and sine functions, you can rewrite this real part of the product of these complex components as the product of this factor times this factor. And what we need is we need the real part of this quantity. So if you look at the products that appear, this one is real valued, this one is imaginary valued, so we don't care. This one is imaginary valued, and this one is real valued again. So if you rewrite this, you get cosine phi 1 cosine phi 2 minus sine phi 1 sine phi 2. So you find a very convenient relation, which means that the cosine of the sum of these two angles can be written in terms of cosine and sines of the individual angles. So let me clean it up for you. When I clean it up for you, I get the relation that I just derived. And it doesn't take much fantasy to realize that if you want to calculate the cosine of the difference between two angles, you can do the same thing. You can use the same trick. You just calculate the real part of the exponent, e to the power I, the difference between these angles. You again write this as a product of exponents, same trick, and you find basically the same result apart from a difference in sign here. And the same, of course, applies for sine functions, because sine functions are the imaginary part of some complex exponents. And again, you find a very convenient relation. So easily derivable with the use of phasors. Another example of the use of phasors is that it allows you to get an answer to the question, what do you get if you add two phasors? So what do you get if you add two arrows in the complex plane? Well, if you sketch them from the rules of addition of complex numbers, you know that you will get a combined arrow pointing in the direction of the average angle. So that suggests that to calculate this properly, you have to take out the average angle. And if you do that with the first term e to the power I phi, you get this expression. And if you do that with the second term, take out this average angle, you get an almost identical term, but with a minus sign here. So if you add these two, what you get is you get the relation e to the power I alpha plus e to the power I beta is a phasor which shows the average angle, and then two phasors which contain the difference angle divided by 2. And these two phasors differ by a minus sign, this minus sign. So if you combine these two and remember the rules of addition of complex numbers, you find the complex number and the complex conjugate of that number, so you get 2 times the real part of that complex number, or this relation. So we find that the sum of two phasors can be written in terms of a phasor with the average angle plus a cosine of the difference angle. So let me clean this up for you. So the trick to calculate the sum of two phasors is to take out the average phasor, and then what you find is that the sum of two phasors is a phasor in the direction of the average, this guy, and the length of this phasor, this length, is equal to 2 times the cosine of half the difference angle. So let's switch to the original topic of the harmonic oscillator. At the start, I showed you that there are various types of harmonic oscillator. One being an object on a spring that bobs up and down, or it can be a pendulum which swings to and fro, or which even moves in circles. And the other harmonic oscillator, which you might not immediately think of, is, for instance, a guitar string. If you take a guitar string and excite it, it oscillates to and fro. So these are all harmonic oscillators. The harmonic oscillation is so common in nature because it describes the motion of an object around its equilibrium. So suppose we have equilibrium at position x is 0, and wonder what will happen if the object is a little bit more to the right or to the left of this equilibrium. Well, because it's an equilibrium, you expect a force back towards the equilibrium point. And if you wonder what is a logical force for the object to go back, the most logical one is that the force is proportional to the displacement from the equilibrium. So this is a logical equation, and then if you think about Newton's law, this force is equal to the mass times the acceleration of the object, so it's equal to the mass times the second derivative of the position with time, or in another notation, x double prime. So we just saw that the equation of motion of the undamped harmonic oscillator is given by Newton's law under a restrictive force of the form minus k over x. And if you divide by m, you can write it in the generic form x double dot is minus omega 0 squared times x, where the eigenfrequency is the square root of k over m. Now, how do you solve this equation? It looks very difficult because of the second derivative on x, but life is easy, fortunately, because if you try a solution of the form of an harmonic oscillator of this form, you find that if you take the derivative hereof, the derivative of a sine, of a cosine is a sine. The chain rule gives you an additional omega there. The second derivative is minus omega squared a cosine omega 2. And as you don't need this one in this expression, and you see that these are very similar, you easily find that this is indeed a solution when you choose omega to be exactly equal to omega 0. So you find as a solution A, the x is an amplitude times cosine omega t. But you can also try another one. You can also try a similar one of a sine form. And you find that the generic solution of this equation for the harmonic oscillator is of this form. So if you combine the two, you get the generic expression, generic solution of this form. If you look at the generic solution of the undamped harmonic oscillator and wonder what determines these coefficients A and B, the answer is simple. They depend on the initial conditions, right? I mean, if you know the position at time is 0 and look at the expression, you see the position at time is 0 is simply A, so that determines A. And if you look at the speed at time is 0, you have to take the derivative of this thing at t is 0, and you find omega 0 times b. So that's easy. Now there is a very nice graphical solution for this expression using the phasors that we started with. Because you can rewrite this combination A cosine plus B times sine as an amplitude, right? This amplitude and a phase of this form. And this cosine with the phase can also be written as the real part of a phasor, which is an arrow in the complex plane. So at time is t is 0, the phase here determines the direction of the phasor, and then if you let time run, this phasor slowly moves. It rotates at the frequency determined by the angular frequency omega 0. So a very nice graphical representation. And if you wonder why we choose a minus sign here, just visit the course. In real life, we rarely deal with undamped harmonic oscillations. In many cases, there is damping. Also, if you have this tennis ball on a spring, you notice that you start with large oscillations, but then as a function of time, the oscillations damp out. So how do you describe damping in a harmonic oscillator? Well, relatively easy. We again look at the Newton's law. The force is the mass times the second derivative of position. We had this restoring force due to the spring, and all we do is we add an additional force, a friction force, which typically is proportional to the velocity. So that means you have a force due to the spring, you have a force due to the velocity, and you want to combine these in a single equation, and let's divide out the m. If you do that, you get an equation of the form the double derivative of x plus c over m times the single derivative plus k over m times x is 0. And this we can write in a standard form by defining a damping rate gamma such that 2 times gamma is c over m, and by defining the eigenfrequency of the harmonic oscillator as omega 0 squared, which is k over m. So this is the generic form of the damped harmonic oscillator, which I write here in a more readable format. So how do we solve this? Well, your first guess might be, let's just try an harmonic oscillation. as we did previously. But then you'll find out that if you take the derivative of this cosine function, you get a sine back. And if you take the second derivative, you get the cosine back again, of course. But if you plug these three expressions in this equation, this sine function is the thing that will bother you, and it will frustrate an easy solution. So at this point, phasors can be very useful, because if you have phasors, then this sine and cosine are both real and imaginary parts of some complex phasor. And so if we try a solution of the form xt is the real part of an amplitude and a phasor of this form, then if you take the derivative and apply the chain relation for differentiation, you get a phasor as x of t, you get a phasor as x dot, and for x double dot, you also get a phasor. And what you see is that every time you take the derivative with a dot, what you get back is a factor e to the power minus I omega. For the double dot, you get this factor back. So if you take these expressions, plug them into this equation, what you will find is that for the second derivative for the double dot, you get minus omega squared. For the first derivative, you get a factor I omega gamma, and the last term has no derivative at all. So then solving this differential equation basically reduces to solving a quadratic equation. And solving a quadratic equation, this quadratic equation, we know how to do it because the solutions for quadratic equations are of this form that you already learn in secondary school, where you get the famous ABC equation of this form. And then if you plug in these numbers for the B and the C coefficients and for the A coefficients, you get this expression. So you find that for this trial solution, this omega in the trial solution has to contain, is a complex number. It contains the damping rate as its imaginary part, and the real part is a frequency which is very close to the eigenfrequency of the undamped harmonic oscillator, but contains a small correction due to the damping. So for the general solution of the damped harmonic oscillator, we found an expression of this form with a phasor, a term exponent minus I omega t, where the frequency of the damped harmonic oscillator is complex and of this form. Now if you wonder what that means in real life, then you can distinguish three regimes, and the first one, the most common, is the regime where the damping rate is smaller than the eigenfrequency of the undamped harmonic system. So that's the underdamped regime. And if you, in the underdamped regime, look at the displacement of the harmonic oscillator from equilibrium as a function of time, you see it's just like an harmonic oscillator, but the amplitude is damped. And the other two regimes that you can have critical damping, where gamma is equal to omega 0, or overdamping, where gamma is even bigger. And in both regimes, you'll find that the position as a function of time decays in a more or less exponential way, but the exponents are different. And in the overdamped regime, the damping can be so large that this evolution is very slow, just as you would have if you have a pendulum inside a sticky syrup. So in this lecture, I've showed you how to describe the harmonic oscillator using complex phasors, and in particular the damped harmonic oscillator. So So the oscillator that oscillates and slowly uses its amplitude. And that was described as a damped harmonic oscillator and can be easily solved with phasors. Thank you for your attention.